Then good morning and good afternoon, and thank you for joining us today. My name is Faye Bastow, and I will be your moderator for today's webinar. Today we'll be discussing trends in mine water management, a crucial topic in the context of a clean energy transition. Our goal is to provide you with insights into current industry trends and some global examples of best practice. Lucy, if we move to the next slide, please. I'm joined by two of my colleagues. Let me introduce them briefly. Eric Schrammel is the Industrial Market Sector Lead for Canada. A professional mechanical engineer by profession, Eric has 32 years experience working in heavy industry, 15 of those in the mining sector. And Lucy Pugh is the Global Industrial Water Practice Director with more than 35 years experience in industrial wastewater treatment and reuse. Lucy's role involves designing processes and treatment systems that remove conventional and hazardous chemicals from industrial wastewater streams. As industries seek to be better stewards of water and the environment, Lucy, Eric and their teams at AECOM are helping mining clients reduce their water demands and achieve zero liquid discharge. So a little bit of housekeeping. Our webinar will run for 45 minutes. We'll begin with presentations from Lucy and Eric, followed by a Q&A. If you have questions throughout the session, please type them in the chat and we'll address them at the end. Lucy, over to you to take us through the agenda.
Great, thank you so much, Faye. I'm having some trouble coming onto camera, so I apologize for that. But just a brief agenda for today's webcast. We're going to be reviewing some trends in the mining industry that are driven by some new technology trends and other things that are happening in the industry. And then Eric is going to be reviewing water management in the mining industry, including some quality and overall flow considerations. And then we're going to wrap things up with a couple of case studies. So the clean energy transition is really gaining momentum. Many energy companies are looking to provide new sources of clean energy, and these clean energy technologies, including solar and wind, battery energy storage, hydrogen production, carbon capture, all require the use of various metals and in some cases rare earth elements. The transition to these clean energy technologies is increasing the demand for these materials, and the copper demand alone is expected to increase by 50% over the next 20 years. The increased demand for these metals and minerals is driving some new approaches to the mining industry. New sources of ores are being explored with a shift from oxide ores to sulfide ores, and the sulfide ores have their own water management challenges that Eric is going to be talking about in a moment. It's also becoming more cost-effective to extract metals and minerals from non-conventional sources, examples being lithium extraction from brine sources, reprocessing of legacy mine waste materials to capture the residual metals and minerals that are present in those waste materials, recovery of minerals and metals from consumer wastes, and also mining companies are trying to optimize water use with the mines, both for sustainable operations and also for environmental protection. Water is used in just about every aspect of the mining processes, including the mining of the ore and the processing of the ore and mineral and metals recovery. And as the water contacts the ore and is used in the processing, it becomes contaminated with the materials that it contacts, including acid mine drainage from the mine waste, the chemicals that it contacts in the ore processing and metals extraction processes, and also the waste management. Mining companies are increasingly focused on environmental, social, and governance considerations as well. Many mines are located in water scarce areas where they may be competing with the water resources with the surrounding communities or agricultural uses. And that's driving the mining industry to consider non-conventional sources of water like saline waters, and certainly it's encouraging water reuse. In some cases, mines are located in coastal areas that are driven by climate change. Very high rainfall events may result in exceeding the water storage capacity at a mine, and that's driving some changes in the overall water management. The environmental regulations for discharges of water from mines are becoming increasingly stringent. Many regulatory agencies are limiting the amount of salts that are discharged to waterways. So discharges for dissolved solids, constituents like sulfate, selenium, these are all driving the use of advanced treatment technologies for the mine water prior to discharge. And then finally, mining companies want to be good neighbors to the surrounding communities, to the indigenous populations that may be in the neighborhood of the mines. And this is driving the approach to the mining operations and also water management. This map illustrates the locations of major mineral deposits across the globe. You can see that they're distributed just about everywhere on every continent. And then this map shows the distribution of critical minerals across the globe. Companies and countries are evaluating the sources of these critical minerals, many of which are used in the clean energy and other advanced technologies. And this is driving potentially some new mining activity in locations that don't currently have mining activity as a way to alleviate supply chain concerns. So now I'd like to turn the presentation over to my colleague Eric, and he's going to be talking about water management.
Thanks, Lucy. If you can flip that to the next slide. So recently, and recently in the last 15 years or so, the usage of water at the sites hasn't necessarily changed, but the management of that water at sites has been undergoing a bit of a shift in how the thought process is going with respect to using it. So at a mine site, you can see water in every single aspect. Just the site itself has a surface area. It deals with storm water. It deals with the snow melt in the spring. All of that water that moves across the site is impacted by the activities on the site, and it needs to be managed. At one time, there was a lot less thought about what was happening to that water that was moving across the site. If you have an underground mine or a pit operation, the mine water is pumped out of those areas, and it's not just the water that comes out is sometimes water that's brought into the pit or brought into the mine for certain uses for underground tools, service garages, dust suppression, but it's also water that's made naturally as a result of the excavation. And that water is influenced by both the activities underground, so diesel fuel, if that's used, explosives raise the ammonia level of that water. And then, like Lucy talked about, acid mine drainage, just waste rock that's present in those areas is changing the chemistry of the water. But that water is dealt with by the mine to maintain operations. So they dewater the mine, they'll put that into a holding area. There's also fresh water, raw water intakes. The raw water is used at mine sites. Sometimes you just need fresh water for housekeeping, maintenance activities, fire suppression, environmental controls, laboratory use, thermal processes like boilers. That water is necessarily taken from a freshwater source. It's not necessarily easily taken from a reuse stream. And it's used in process water in critical areas where chemical certainty of the water content can't be gained. And then water's taken from the area, water's impacted from the area, and then the water is used within the processing areas and sent out to a kind of a buffer zone called the tailings pond or a mine tails area. And tails is just a way of saying a waste stream. It reports to the tails area as a transport mechanism for slurry. It'll take some of the waste rock in a slurry down a pipeline and deposit it into a waste tails area. Even if they use a dry stack tails where they try and dry out the waste product out of the mill, the water that was in the process prior to that still has to be taken care of. If it's not transporting the slurry, it still comes off the top of a thickener in a way that needs to be thought about. So mines, they take the water in from surface, they take the water in from dewatering, they take water in from freshwater intake, they discharge it from the process tails, and in that process tails area, they can reclaim some of the water rather than discharge it. And that's the thought process now that we're getting into that wasn't necessarily given a great deal of time or effort to in all mines without cynicism. What drives a decision is generally cash flow and money or regulatory requirements. And we're seeing now, Lucy mentioned the ESG, that a social conscience or a community good stewardship thought process of corporations is now being pressed in. It does impact finances, it does impact the reputation of a company, and that is causing the companies to think about where are we getting our money from, our money from, our water from, and how are we managing that water, and what is the long-term impact of that water use. If you go to the next slide, Lucy, we talked a bit about acid mine drainage earlier. This is just a quick summary of what acid mine drainage is. So we have the processing of the ore, we have impact of the mining activities on water, and something that you'll hear a lot about in the industry is acid mine drainage. And it's just simply when you pull a rock out, that surface area of the rock, if it has a propensity to interact with the water and create an acid, that is an ongoing process once it's exposed to the air and once it's exposed to rain. It's different than when it's bound in situ. So that is something that is considered heavily when we talk about water flow across the surface of a mine, and we talk about the mine site in general. It's not just processed water, it's water that's impacted simply by the act of removing a chunk of waste out of the way to get at the target rock. So if you go to the next slide, Lucy, you can see the chemistry of what's going on here. So the mining companies used to just take water when they could, if there was no restrictions. If you live in a place that has a lot of lakes and a lot of water, it is easier and less risky to take fresh water, use that water, put it into a tails area, and just almost like an open cycle, water in, water out, and everything is fresh. When you start recirculating water, which they're doing a lot now, the mining companies are really considering the chemistry of all the various phases in their process. They're considering the occupational health and safety implications of reusing water, but they are investing significant amount of money and laboratory analysis in understanding where they can minimize the discharge of water and how much of that water can be reused. So as an example, in a grinding circuit, your overflow water from a grinding circuit, as you thicken prior to a next stage of process, you can take that process water and you can use it anywhere downstream in the process. And as you start adding reagents and as you start adding chemicals, with the right understanding of how those chemicals are maintained in the water, you can really reuse that water. But we're seeing a segregation of water streams now in the mines with the intent all the way along of trying to reuse water where it's logically able to be used and it's not detrimental to the process, because water is being recognized more and more as a precious substance. There are still streams that have to leave. There are times when, as you're recirculating your water load, you have to bleed some water out just to get rid of some buildup of chemicals or minerals that are dissolved in that water. That is treated obviously before it goes anywhere, but those streams are shrinking and shrinking and shrinking. There's also some water that's lost to product. If you ship a concentrate from a site, even if it's 5% water, it's still 5% water, and that water needs to be made up. And there is some potable water that comes into the system as a necessity for laboratory use, process analyzers, personnel. But this table that's in this is just a good example of water that's passed through just in contact with a mine without any consideration picks up minerals very quickly. So if you go to the next step, we talk about the money and the investments being made by the mining industry. Technology is advancing significantly, and process interactions are being understood at a much more granular level than it used to be. And we're seeing interstage treatment of water. We're seeing a real thought process of let's clean this water up enough that we can reuse it here. If we have to treat it, let's treat it for our own internal use rather than taking fresh water. There's a lot of technology that's changing now, and just understanding on the long-term implications of what's going on in water. When I started in the industry, as I noted, it was not at all unusual to not even think about where the water was coming from. It was just there. And now the very first step that we see, one of the very first steps that we see in a mine study will be an identification of the water balance for the entire site, as well as the water balance for the process. And then we talk very specifically to the laboratories that are running the metallurgical process testing about the chemistry of the water that's coming out of those processes as well, so we can understand how to reuse that water back. It's questions that were not asked, certainly not asked 20 years ago when I was in the mining industry, 25 years ago, not at all. And now in the last 15 years, we're seeing those questions. So I have a couple of case studies. It's not exhaustive, but it gives you two very different mining thought processes, things that you might not even think about. We're looking at a mine quarry, which is simply just a sand quarry, and it was they're going to mine sand for solar glass, and solar glass is one of the new energy driven products. And I think we all think about solar glass panels and what an environmental godsend they can be. We don't necessarily think about, and we wouldn't have thought about in former times, how clean the sand needs to be and how to get the sand to that level of cleanliness. So the company that was taking a look at this, they're in a very northern region. They're next to a parkland, a federal park. They're in a very water rich area. There's no risk of running out of water, but the water in this area are traditional fishing grounds and commercial fishing grounds. There's an indigenous community right next door. And so the very first step that was taken was to engage with these communities, to look at the environment, and actually to agree at the outset that this would be a zero discharge mine. And I can tell you that there's a cost to that decision, but it wasn't even up for debate, just in this new mindset of how things would go. So the resource that's there has one of the contaminants that they have is iron, which is pretty detrimental to solar glass. Solar glass has a very tight quality for sand that they want, and there were two ways identified to get rid of the iron. One of them is a chemical means, which would have made zero discharge almost impossible, and there was a mechanical means, and they invested a significant amount of money at a microscopic level, identifying the possibility that the iron was bound to a certain size of sand particle, and they were able to design their process to mechanically scrub the sand, get the iron to fall off at a certain level, and any iron that wouldn't fall off was bound to larger particles. They actually increased their waste stream of sand. They identified an alternate market for that sand, not as lucrative as solar glass panels, and kept a smaller portion only for the solar glass itself. But it satisfied it satisfied the responsibility that this company felt to the long-term potential impact to the waterways, the fisheries, the parkland, the indigenous communities that are there. They chose that right from the onset, and all of the testing from the get-go was done to focus on that avoidance of chemical introductions to the process of the sand. Small project, but a big, kind of, it would be strange to produce something environmentally forward-looking like a solar panel at huge environmental impact to the environment, and they didn't want to be that group. If you go to the next one, more of a traditional base metals mine. This mine operated, I'm going to say, for almost 100 years. I'm probably off a little bit there, but it has been around for decades upon decades, and it was one of the very first mine sites I went to in my career. You can see the colors on this slide representing the tailings areas, the waste discharge streams. The mine collects, as a result of its history, it collects stormwater from all of the adjacent properties. They are not at the high point in this region that you're looking at. Any water that flows onto that site is impacted one way or the other. Any of the snow that accumulates on this area is impacted as it melts one way or the other. They treat, or have treated for the last few decades, the water on this site has a lot of dissolved metals, and they treat it by raising the pH, settling out the solids, and then neutralizing the water before discharge. They test it and they discharge it back into the watershed, but it's a lot of chemicals added to combat heavy metals. They're very aware of the long-term implications of what's going on here. And so as they're starting to ramp down operations at this site, they actually ask some questions which I believe I know for certain at this site, wouldn't have been asked 30 years ago at this site. They wanted to understand if there was a way to relieve the permanent and ongoing impact to the watershed, potentially, right? I mean, you have to treat your water for forever as it washes across this site. So they started taking a look at the old tailings, and they started thinking about it as a resource, don't get into a stock market resource discussion on this, but they looked at it as the technology for processes changed so much that all of the inefficiencies that were in the processes to this date have left minerals unreclaimed in this tailings pond, and it's those unreclaimed minerals that are impacting the surface water that flow across it. The question that was posed was, is there a way that we can have this cleaned up to a neutral, non-acid generating, able to be capped mine waste area, so that it's stable for the long term, it no longer has any influence on the surroundings, and have it pay for itself to do that. And they've invested a great deal of money in testing. They've gone through I think they've gone through from 1990 onwards, the metallurgical records on the process. They've taken a look at the metallurgical balances. They understand what's in these tailings. They've drilled to confirm. They've analyzed it with the most recent they've analyzed it with the most recent technology for extracting the metals, and they believe that they can extract a lot of minerals from what is there, sufficient to neutralize it, so it's no longer acid generating, and they can bring it to a dry, stackable, cappable state. In a minimum cash neutral. They actually think they may make some money on this. It's very early stages, but the amount of money that's being invested just shows a change in mindset, rather than walking away from this tailings pond and just doing the easy treatment. It's just a different way of looking at the problem from a long-term perspective. I think that's it for me. Lucy, I think you have a case study as well.
Yeah, thanks, Eric. Those were really interesting case studies. Yeah, our final case study is the Giant Mine. This is a gold mine, closed gold mine, located in Yellowknife, Northern Territories of Canada. During its operation, it generated over 7 million ounces of gold. Arsenic trioxide was produced during the gold extraction process, and this waste material is stored underground throughout the site. and it has, through inflow and groundwater infiltration, impacted the mine pool water at this facility. The mine pool water needs to be pumped to maintain its level, and it's discharged to Yellowknife Bay. And there is a water treatment system currently at the site that includes chemical treatment and some settling ponds. But because of more stringent environmental regulations, a new water treatment system is required at this facility. So this is a mine that is impacted by climate change. The receding permafrost at this facility has contributed to additional groundwater movement and seepage and additional contamination. So one of the things that we're doing is there will be thermal siphons that will refreeze the waste material to minimize its movement and impacts to the mine pool water. For the water treatment system, we were talking about how the significant impact of stormwater at these mine sites. So one thing that we're doing is reducing the inflow to this mine site by redirecting the stormwater runoff. By doing that and by filling some mine pits, we're able to reduce the hydraulic capacity that's needed for the new water treatment system by half, so very significant. The new treatment system is going to include some new reaction tanks, clarifiers with solids recycled to minimize the chemical addition that's required. And then the clarified effluent will be filtered and will be polished with an arsenic removal media to achieve a 10 microgram per liter arsenic limit prior to discharge to the bay. Our Stephen Pickle was in charge of this design, and it just started construction. It should be operational in 2026. So just to kind of summarize and our discussion today, and also what we learned in the case studies, the demand for base metals, rare earth elements is increasing as a result of energy transition, and the approach to mining is changing because of ESG considerations, climate change, and just the increased need to reuse water at these mines, as Eric was talking about. Mining companies are increasingly focused on water stewardship, both to meet stringent environmental standards, but also to reduce the water discharge and reduce long-term impacts from the mining operations. And the great news is that all of these changes to the mining industry is resulting in some innovations, including recovery of metals and minerals from unconventional sources, technology advances, as Eric was describing, to recover some of these trapped minerals in legacy mine wastes, and then just overall improved water management. So thank you very much. That concludes our presentation, and I'll turn it back over to Faye now.
Thank you, Lucy. Thank you, Eric. I've got a couple of questions that we had received in advance, and then I'll go to some of the questions that have come through on the chat as well. So this question's for both of you, really. You talked about the clean energy transition. How is this manifesting in your work?
Do you want me to start on that one, Eric?
Sure, go ahead, Lucy.
Yeah. So we're certainly seeing a lot of changes involving lithium extraction from brine materials and the technologies that are being developed to be able to accomplish that. And it is becoming more cost effective. And then just the energy technologies themselves, including carbon capture, a lot of activity with respect to hydrogen generation and how that relates to water and even wastewater. So there's really been an uptick in activity across all of those sectors.
Yeah. And I think we're seeing with the clean energy transition, it's not to push it to a gold rush mindset, but as the clean energy transition starts a demand or pushing the demand for rare earth elements, we're seeing a lot of previously not viable projects become viable and being pushed, trying to capitalize on that market interest. I mean, it is a business at the end of the day. And what the major mining companies are are certainly on board for keeping a focus on that ESG mindset, the context of a good neighbor and good stewardship of a resource. But some smaller junior mining companies also have a vested interest in getting their mines coming to production. The studies are being pushed through, and we want to keep that focus still and just keep reminding people that there are now understood to be longer term implications, and we're trying to guide that water stewardship mindset, that minimizing impact on neighbors. But it is, I mean, any surge of demand drives and produces far more mining projects always.
Thank you, Lucy. Thank you, Eric. Another question then about the amount of water used in mining. Can you both comment on the progress in reducing the amount of water used in ore processing specifically?
Want to take that one, Eric?
Sure. I don't know that the amount of water has reduced so much as the amount of freshwater consumption has reduced. So when I look at, I'm going to say it in the wrong units. I apologize to everybody, but when I look at a modern mine that consumes 200 gallons a minute of fresh water, they are recirculating about 1,000 or 1,500 gallons a minute of reclaimed water, and then internal to the process, they are up in the 2,000 to 2,500 gallons a minute just in each stage of the process. And it's that recirculation of the water that really reduces the makeup of water. So now we're seeing when you leave the site, if you leave with a concentrate at 10% water, you're just losing 10% of that water. Your tails are transported out with 30% water to them or 40% water, but that water is coming back in a reclaimed fashion. It's not being made up anymore. So I think that the grinding and the flotation and the hydrometallurgical processes are all still consuming or still using the same amount or same volume of water, but they're not releasing that water in a open circuit type of thought process anymore. There's I would say maybe without scientifically calculating it, my gut feel says between 5 and 10% fresh water makeup now.
Yeah, and I guess I'll just add, you know, the giant mine example, just being more mindful of the impacts of stormwater on the mine overall water management, just being more mindful of that and controlling that to the extent possible. In the giant mine case, we were able to reduce the treatment requirements for the water that's discharged by half. So that's pretty significant. That system is designed for 400 gallons per minute. So it would have been, you know, more than 800 gallons per minute without those controls.
Thank you both. Next question they've received on the chat then is, do you have any experience or knowledge about using nanobubbles, air or oxygen, to clean up the tailings?
I do not. Lucy?
I don't either. We have a lot of experience with nanobubbles, but I'm not aware that we have applied that technology for tailings. But we can certainly look internally and get back with you.
Thank you. And here you can explain your, I suppose, your Dear Santa list, if you like. What's on your research and development wish list of items that would be able to help better support the energy transition better? For example, passive water treatment, cheaper characterization. What would be on your Dear Santa wish list?
Well, I love the idea of passive treatment. I mean, that applies more to the mining industry, I guess, than the clean energy technologies. But passive treatment, if we can make that work and if we can achieve the limits that are required, you know, that has the opportunity to reduce a lot of cost in the treatment process, a lot of requirements for operational attention and maintenance. So I think research into passive treatment would be fantastic.
Thank
Eric,
you.
you mentioned a couple of examples. I was just going to say, Eric's mentioned a couple of examples for his case studies where there's been research into mining operations to recover metals and minerals. I think that's a great area of research as well. You know, we have all of this waste material that still has value. What can we do to maximize the value for those materials?
Thank you, Lucy. Moving on to the next question then. With an increase of closed loop water management systems, is there any industry exploration of energy recovery from the in-pipeline hydroelectric energy potential?
You know, not specifically. I know we looked at that back in the early 90s. There is a project underway in Australia, and I within our own company, and I don't know the details of it, but they are using an old working to generate hydroelectricity using an abandoned mine shaft. And it's not so much that it is producing energy from nothing. Generators are inefficient, and but it is an offsetting of cost, right? So during peak periods, electricity costs so much, and during non-peak periods, it costs less. And I believe that they're offsetting peak and non-peak electricity costs by using that old mining, the old mine workings. I don't know if they are transferring the water below ground and leaving it, or if they're bringing it back up to surface and there's only a small net gain in cost offsets, or if they are using the old mine workings. We have some clients that use the old mine workings as a storage area as well.
Thanks,
I don't know
Eric.
if that really answered it.
Thank you. And next question, has grouting been utilised to help lock the waste in place that the thawing of permafrost has freed?
I don't know the answer to that for the giant mine case study. Eric, do you happen to know?
They are using a grout program at the giant mine, but I don't know that the grout program is meant to lock anything in the water so much as to have a more efficient retention of freezing in the ground as they freeze it up. So if you have a water base flowing around your frozen section, you have to fight more to keep it frozen. I believe they're using a grout program to block off some of those water routes underground as they start to freeze things. But I don't believe the intent of it at that particular project was to lock any contaminants in place. It was more to make the freezing of the ground more efficient.
Thanks, Eric. Another question for you. What type of media could be considered for AS removal? I hope I'm reading that correctly. And if you could let me know what AS is also, please.
Yes, yeah, that's arsenic. So we actually did some pilot testing of 3 types of adsorptive media for the arsenic removal, and selected one. I don't know if I'm allowed to say the supplier's name for that media, but it was based on pilot testing, and it is a adsorptive process that's being used.
Thank you, Lucy. Another question then that we had pre-submitted while I wait to see if there's any others that come through. Can you give me an example of new information or intelligence that challenges conceptions about the impact of mining?
I can. I'll keep it kind of vague, and to me it stood out. So years ago, regulatory changes took hold. I would say in the early 90s. I think it was the early 90s where they realized that selenium was a negative impact of it. It's something that had a much more greater impact than originally anticipated. So this particular mining company stopped discharging selenium to a lake, a nearby lake. 100% they stopped. And they took an exhaustive monitoring program to just make sure that the selenium was no longer in their tails, that there was no longer any passage to selenium being added to the lake. And they took fish selenium content testing, and everything seemed good. The expectation was that over the next 20 or 30 years, that the selenium levels would decrease. I don't know. They wouldn't be there, or they wouldn't get worse. And recently, there was some fish caught, and I'll read you the statement that was issued to the public. It says, even though selenium concentrations have been decreasing in the environment over time, the effluent and remain stable in this lake, selenium in the fish tissue is increased in samples collected in 2020 compared to 2008 and compared to 1990s. They're looking at northern pikes and white suckers. Both of those fish are showing quite an increase in selenium concentrations. And it kind of took them by surprise. There was no expectation. I don't know if it was just a hoping for the best expectation, but there was no expectation that something that was thought to have been addressed in the early 90s would actually culminate into a worse situation from a fish perspective 30 years later without any additional contribution of contaminants from the mining industry. And it just shows, I think, the long-term impacts that intuitively you might think it's dealt with. 30 years later, we were kind of surprised to see, wow, we thought we dealt with it and it's getting worse.
Thank you,
That was
Eric.
in Manitoba, I believe.
Thank you. That's really interesting. And one final question that's just come through on the chat that I think we can squeeze in. With respect to recovering metals, is it more valuable to selectively recover specific constituents, or is it more preferable to simply remove excess water volume, leaving a more concentrated solution that contains a mixture of dissolved solids and metals?
We looked at that, depending on why the question is there. So in the mine water, they have dissolved metals, and we precipitate out those metals without any intent. At the case study that I looked at, there was no intent to recover the dissolved metals, only metals that are still bound in the tails. We looked at evaporating the water using not thermal evaporators, but atomizing technology, spray it into the air and maybe get a 30 or 50% evaporation rate, a little harder in northern Canada. And that concentrated down the metals in the volume of water, and theoretically it reduced the size of our treatment plant. So there was a capital offset looking downstream at the size of the treatment plant if we could keep up with water generation in the ponds. But the cost of treatment was still the same. The amount of reagents and chemicals to drop a concentrated metals out versus a more dilute metals out, the amount of reagent required was still the same. It was just a smaller volume of water being treated. So the physical plant reduced, but the cost for chemically treating that plant, we found, was about the same. And it didn't kick the feet out from underneath considering evaporators. I believe that's still on the table and is something they're going to try, but it didn't reduce the treatment cost, only the capital investment in the treatment plant, if that makes sense. I don't know if that's what the questioner was asking.
Understood. Thanks ever so much, Eric. So in the interest of us finishing on time, I'm going to close the questions there, and thank you, Lucy and Eric, for those truly insightful questions and for those great responses to those questions. We've covered some really important aspects of water management in mining operations today, including advanced strategies, regulatory impacts, and the importance of ESG considerations. So really thank you to you both for sharing your expertise, and to everyone today who's participated, asked questions, joined in and listened, for your active participation in today's session. And I know with the recording and the PowerPoint or PDF will be shared post this. Lucy, Eric, anything from you as we close?
Yes, I would just like to thank you, Faye, for moderating. I'd like to thank the WEF folks for hosting this webinar. We really appreciate this opportunity, and also to everybody that attended today. We are just thrilled to have you join us for this webcast.
Yes, thank you everybody for your time. I realize it wasn't exhaustive. It's a very short time frame, but we thought it would spark some thoughts and conversation.
Thanks, Lucy. Thanks, Eric. Thanks, WEF. Thanks, all the participants. We shall close it there. Bye-bye.
All right, thank you, everyone. This actually concludes today's e-showcase. Thank you all for attending. The recording will be available at webfiresguide.web.org. We will send all registrants an email tomorrow with that link, and please visit our event calendar to sign up for future webcasts.